Okay, so welcome to this modeling and simulation of materials course. This is for the graduate students, but some of the senior undergraduate students are also allowed to attend this class. Here this course time is a little bit unusual. The Tuesday 3 to 5:45 p.m. So these two courses are actually combined into one day. And this is because this is actually team teaching with the Professor Satoshi Watanabe in University of Tokyo. In the way of, because in University of Tokyo, this course is actually the 2-credit system. So we are 3-credit system. So UT starts from the April. And this first month, we only, the SNU students are going to attend this class, but some of the students in the UT will also see the video file, the recorded video file of this lecture. And Professor Satoshi Watanabe will join this course from next month, April. And so in tuning our time, we decided to, this is the only time that we are actually available for us to have the enough amount of the course days, because the most difficult thing is that the two countries have a different holidays actually. For example, in the Buddha's birthday we have a holiday, but Japan, they do not have such a kind of the holiday. And so because of that, this Tuesday is the only day that also we can have enough amount of the time. Okay, as was announced, this is team teaching between the Professor Watanabe and me, and actually we are a long-time friend. Okay, long-time friend. I know Professor Watanabe since I was in a graduate student, and we have a very similar field. He's also doing the quantum mechanical, the quantum materials modeling, and the same for me. And so we are, some of the work we are collaborating with each other. Okay. And interestingly, actually this team teaching was announced, appeared was advertised in some of the internet newspapers, because this is the first time. There are many courses between the remote lectures that, for example, the professor in SNU give the lecture, and this is streamlined to the UT students. But usually the single professor fully in charge of the one semester course. Okay, but this is the first time that we have actually try this kind of a team teaching, that some part of the course is given by SNE professor, and the other part is given by the UT professor. This is the first time that we try this kind of team teaching between the two universities. So the College of Engineering, they decided to advertise this team teaching. And so if you look at Hansungu, Dokyode, then you will find some of the internet newspapers, including Yeonam News, they have some very short description of this. Maybe I can find it here. All right. All right. So let's first go to the google.com. And then, all right, so, okay, and this was advertised, okay. It's the first time that simultaneous, but it is the kind of team teaching, but I don't know what they mean by this simultaneous remote lecture, but okay. And so I hope you to be proud of this class, okay? And I'm also happy that so many students from different groups, not just material science, but also chemical engineering, mechanical engineering, and maybe in the natural science. And I'm very happy to see so many students from different areas, and they are interested in the materials modeling, okay? All right. And some brief description of the course is that well, my lab is materials data and informatics laboratory. We are doing the computational simulation mainly. And this is my email address and phone number. And my office is the building at 33 over there. And this is the thing that you have to, maybe you have to write down on your notebook today. This class homepage is, if you visit our lab homepage, mtcg.snh.kl, and you click on the lectures, and you find this model simulation of this course, and the same login and the password, MSM 2018, then every materials necessary, for example, the assignment, the lecture materials, and also the first, this month, the courses during the March, they will be recorded for the students at the University of Tokyo, and they will be uploaded through our webpage. Okay? So please visit. So everything, including this introductory materials, will be uploaded after this class. And I will try to, from the next class, I will try to upload this lecture material before the start of the course. And so you can download the file and print it out, and maybe it will be helpful for you. All right? I encourage you to print it materials before the start of the class. And we have the two teaching assistants over there. Jung Won-seok, please stand up. All right? Okay. Jung Won-seok, please give him applause. Okay, you can. And Dong Sun-yu over there. Okay. So they are very much they are very much have many experiences in the computational modeling, so they will be fully entitled to assist you in various topics. All right, and the email for the representative email is msm2018.ta@gmail.com. So if you need something, some assistance or some questions, then you can send an email, and the teaching assistant will check them and answer it to you as soon as possible. All right, and their office number and this phone number. All right. And the course layout this is on the syllabus already. It consists of the three parts. So the first part, which is given by me from the March 6th today to April 3rd, okay, for the 5 weeks. Okay, and so this will cover basically the classical molecular dynamics simulation using the LAMS package. All right, so there's no quantum mechanical part here, and we only deal with those classical molecular dynamics simulations. And we first, after running about some of the basic concept of the MD simulations, then we will discuss about some of the simple applications at the 0 Kelvin and also the finite temperature properties. And except for today, but today at the end of the class, about 20 or 30 minutes, the TA will show you how to install this LAMS package. The LAMS package is the free software. You can download it and you can install it on your own laptop. And so they will show you how to install and how to learn it, the basic stuff. And from the next week, every class will consist of the two parts. The first part will be about the theory about the relevant topics, and the practice session is the second. The second part of the course will be about the practice session, and you will learn the program on yourself and see about and analyze the result, etc. Okay. And so on the syllabus, I asked you to bring your laptop, maybe not today, but from the next week. So everybody can do that, can bring your laptop, the decent laptop, to learn the program. Everybody can do it, or any students have some difficulties in preparing the laptop. So 다 노트북 가져오실 수 있나요? Okay. So if you have some of the difficulties in preparing the laptops, please ask me or ask the TA, and they will help you. Maybe you can lend from the this computing center in our university, or maybe we can prepare our own laptops from our group, couple of them, and so maybe we can help you. And so, okay, don't hesitate to contact with me in case you do not have a decent laptop. All right. Okay, so that's the end of the first part, and the second part is given by Professor Satoshi Watanabe in the UT, and so it will streamline it through this internet, all right? And he will, this is mainly theory stuff. He will basically explain the basic theories and the basic the applications of the quantum modeling, okay? And but some of the topics can overlap slightly with this first part. In that case, I understand that Professor Watanabe will also change his stuff to be to avoid those redundancy. All right, and Professor Watanabe will visit here at CNU on April 17 or May 1st, and he will give a lecture here, okay, to interact with you directly, okay, not in real person. Okay, so he will come here in one of day. And the last part 3 is about the practice session about the quantum modeling. This is given by me, and also this will mainly about this is the mainly the practice session. Or similarly, I will give the explain the basic theory in the beginning, and you will learn the program on your own. Okay, just like that. In this case, the package that we are going to use is called the VASP, V-A-S-P, I didn't write it here, but Vienna Ab initio simulation package, which is the very, very famous package that is used for the quantum materials modeling. Some people say that, almost maybe half of the supercomputers in the world, they are actually consumed by the learning this program. So there's so many groups over the world they are learning this program, and this is the standard, almost a standard evaluation package. And so we'll learn this program, but this is so much demanding calculations, and so maybe you will not be able to. First of all, this is not free software. This is the commercial software, and you have to. So in the university, if you are in the academic institution, then you have to pay like. 2천만 원? Okay, 20 million, no, maybe 10 million or 20 million, something like 10 million won, not dollar, for each package. And and it is also very, very computationally expensive package. So maybe even if you can install the software on your laptop, it will take maybe some days to complete the program and complete the calculation. So in that case, maybe we will prepare maybe some of the resources within our own clusters, local medium-sized SPOC clusters in our laboratory, and maybe try to. But I'm not sure the 30. So in total, how many? Let's. Did you 해봐 총 몇 명인지? 35. All right. It's super challenging. Maybe we have to empty all our resources. All right. I don't know. Okay, so I will try to make the separate account for each of you to learn the program in a reasonable time, to complete the program in a reasonable time. All right. So that's the and also fortunately in the UT side, the Professor Watanabe mentioned that they can also this BASF is available to every students for the limited of the time for the students in the UT. So we can use this package for the practice session of this quantum materials modeling. Okay, and we deal with many different topics that is specialized for the quantum simulations. But I pretty much doubt that we cannot cover all of these topics. Each topic is so much takes so much time to fully explain everything. So, all right, but I'll try to cover as many as possible. Okay, and in the meantime, I will visit to UT for one day, maybe June 20 from the current schedule. All right, so that's the basic course layout, and the evaluation for our part. maybe I'll give you 2 times of the test and about 6 times of the homework. This is approximate number. And also maybe the term project, maybe the group. You can make some of the 2 or 3 of you can form a group and prepare for the term project. Okay, and then we will have some day that is dedicated to giving this term project presentation. All right, that we'll discuss later. Okay, so that's it. And about the textbook, there's no specific textbook. Most of the materials, every material is actually I prepared on my own. For the reference, there are good references for depending on the topic. And about this book, the Computational Material Science, it covers many different topics very briefly. Okay, not just the classical, but also the quantum simulations and microscopic simulations. And this is a good guidebook. And about the classical and the simulations, maybe this is the well-known textbook by the Dean Frankel, Understanding Molecular Simulation. This is a very good book, very exhaustive book. But it is specialized on the molecules and also the liquid systems rather than solid-state calculations. All right. And about the quantum calculations, in fact, there is no good textbook for the quantum simulation because it is so much, it has so many layers of the theory and also very diverse applications. So no single book can actually cover every topic. But this one, the dense functional theory by the Shaw, right? David Shaw. This is a good introductory level textbook. So if you read it, then you can have a very good, introductory level understanding of the dense functional theory or the quantum modeling. All right. Okay. So that's the end of the some of the orientational material. Any questions? Okay, so you can ask in Korean, English. Right? Right? So, okay? All right. Okay. Then we will start. So you can ask question anytime. And I encourage you to make a question. It will make me much more easy to teach. All right. It started at 3. All right. So today we will talk about the basic concept in the classical molecular dynamics simulations. And to begin with, first let me define this. What is computational material science? This is my own definition. Computational material science is the analysis and prediction of mechanical, electronic, transport, growth, and the thermodynamical properties of materials based on the solution of the basic equations for the model system that mimic the real materials. Very wrong definition, but I think it contains every essential ingredient of the computational material science. So first thing, the most important thing is that we mimic the real materials. So depending on your research topic, you have the material system that you are interested in. It can be a battery, or it can be a solar cell, or it can be a semiconductor. All right, there's some real materials, and you want to simulate something. All right, but you cannot directly. So this is simulation. So basically, it is not a real system. All right. So first thing is that you have to make a model system that represent that best mimic or mimic the real materials, all right? And once you build out the model system, then there is an equations, the governing equation or the basic equations or the constitutive equations that actually dictate the behavior of the model system, all right? And so then you have to, using some of the numerical analysis or the computational technique, you solve it. Okay, we do not solve it by hand. We solve it by computation. All right. There are many, the the well-known theories of each of type of the mathematical equations. All right, and then you solution. All right, and you interpret your solution. Sometimes your solution is directly give you what you want, like what is band gap or what is the the thermal free energy of the system. But if you sometimes the solution directly gives you the quantity that you want. But in many cases, you have to reinterpret your solution to connect what you are actually interested in. All right. So by the analysis, that you can understand what happens in your system, or sometimes you can predict its behavior before you actually doing the experiment. All right. So these two activities, analysis and the prediction, they are the very much of the pillars, the important pillars in the computational material science. All right. But in many cases, most of the applications, you actually use them to interpret or analyze or understand what happens in your system. All right. That's what we are doing in many cases. All right. So the computational material science, there are many different methods within the same within the computational materials modeling, and you can distinguish them depending on the size and the time scale that is actually adequate for each the method. All right. So in the case of the finite element method, or in Korean 유한요소 해석법, in this case you can deal with very over the wide range of the scale, like down to nanometers. Maybe nanometer is not so much interested, but up to millimeter or the meter scale, or even you can simulate the whole building of this size, so several tens of the meters. Okay, so it can cover a wide range of the scale. And about the time scale, you can simulate the sum of the second time or hour time or the following. So this is most realistic in terms of the size and the time scale. This is finite element method. But this does not take into account this atomistic picture, right? So everything is just continuum, right? You do not see every atom. This is just a continuum scale. I will explain that in the next slide in more detail. And also, but in the other extreme, there is a quantum or classical molecular dynamics, which belongs to atomistic simulation. Okay, here you look at each atom, you distinguish each atom, and you try to simulate, or in the case of the quantum simulation, you distinguish atoms, ions, and electrons. And you describe the motions of the electrons or atoms, okay, using the equations, like Newtonian equations or Schrödinger equations. All right. So this is the most basic, most fundamental type of the equation. So everything just consists of the atoms. So if you know how the atoms will move or electrons move, then this is everything that you need. All right. But the problem is that since you are dealing with so much details, you can deal with a very short time scale, or like short times like up to nanosecond. Or in terms of the length, you can deal with like up to maybe 100 nanometer. That's the maximum that you can deal with. All right. This is so much tiny time scale and a tiny size. But once your simulation model system can fit into that region, then you have a pretty much good tool to address to look at the very much small the details of each atom. All right. And there is also the mesoscale, or so-called the core. It's not really like continuum simulations, but okay. So the coarse grain, not the grain, not this grain. Maybe the E is missing here. The coarse grain simulation. So, for example, if you want to simulate the protein, okay, and the protein consists of the amino acid sequence, right? Maybe dozens of the amino sequence is comprise one the protein, the polymer. Okay, so in the atomic simulation, you look at everything. You distinguish carbon, nitrogen, oxygen, and hydrogen, right? But in the coarse-grained simulations, you treat one amino acid, just one, like some models, like some one bead or some one spear. Okay, so each bead can, somehow use can change its shape or the distance or the angles depending on some certain potential. And so instead of looking at the atomistic details, you take some of the regions. Take that the region, just one part. That's the coarse graining. Okay. So in the mesoscale simulation, by coarse graining technique, you can deal with, for instance, the very long polymers, for example. So it is very favored method, especially in the chemical engineering. All right. So this course is mainly about this quantum and classical dynamic simulation, so atomic simulation. But since this finite element method is so much powerful and widely used in various researches, so let me spend some time to introduce this method in more detail. Okay, so for instance, if you want to obtain some magnetic field in the presence of the magnetic material. So for this material, so the system is that there is the ring, this iron, the cylinder with empty cores, okay, and there is and besides this iron cylinder, there is two sheet, the current, electric current are flowing in the sheet form, right? And so you are just cross-section of the system, okay? And you want to calculate in the presence of some of the current density that is passing through this conducting wire coil, what is the magnetic field distribution of this system? That's the question you want to solve. And so in this case, the governing equation or the constitutive equation is basically the Maxwell equation, right? The curl of the H is equal to free current density, and also the divergence of the magnetic field is 0. Okay, and the B and H has this relation. This mu, so in the vacuum, this mu, the magnetic permittivity is mu is not, but inside the material, it has a very big, large, very different value. All right, so it depends on this mu, depends on the position. All right, and so this is the basic, the differential equations that you have to solve. And in addition to that, you have the boundary condition. Like at the boundary, the magnetic field is continuous, the normal component is continuous, and tangential component is continuous, something like that. Okay, so you have some boundary condition that's imposed on top of this governing equation. So this is the real system. This is the model system, and this is the equation that builds upon that model system. Now, so in the finite element method, instead of solving this directly, it actually to separate or disintegrate the whole space into some of the finite element. Okay, this is a mesh. All right, and it solves this equation using the technique that is well known in finite element method. All right, and it's very fast, and it can be efficiently doing. It can be very efficient. There are many efficient techniques to the calculations in fast, and the result is on the right. Okay, so that's the magnetic field line. All right, so this is a very basic type of the finite element method, and there are many good commercial packages that can carry out this finite element method. If the MATLAB or the COMSOL or the Abacus, they are all the similar tools that can solve this equation with the finite element method. And or in the semiconductor industry, in electronic materials, there is well-known the package, so-called the TCAT or technology computer-aided design, that in the semiconductor industry, before you actually manufacture your device, the first they simulate its properties. Okay, for instance, this is the transistor structure, and
they want, before actually the process or the dope this silicon wafer, they go through this kind of the simulation. So the process simulation, that you simulate this how this dopant diffuse. Actually, sorry, that this is the wrong equation. These are completely different equations actually for the 5-stream model for dopant diffusion. So there is something like similar to that kind of the differential equations. By solving that such a dopant equations, then you can predict how this dopant will diffuse at a certain temperature, right? And also on the right hand side, this is the IV characteristic. So this is the once you make this kind of the transistor, if you apply the voltage, then this this is the current that you obtain from that device structure. This can be also obtained very efficiently by solving the drift diffusion equations, right? So in the semiconductor industry, so before actually design these device structures, they first go through many different iterations of such simulations, and they decide their final device structure, and then they actually manufacture it on the web, using the lithography technique. Okay, so such an finite element method is widely used in the industry. It's a very much powerful tool. And if you are interested, then in our department, Professor Yoonyeol Woo 교수님, he is actually he's an expert in this finite element method. So he has his own the course that is dedicated to the finite element method. So please look at that if you are interested. All right. And so about these atomistic simulations, let me show you one of the example. This is about the position of the organic molecules. So in your smartphone, there is an OLED display, organic light emitting display. And when you make it, you will deposit small organic molecules and to make some of the layer structures. Okay? And this simulation actually shows such a deposition process. Okay, so a different column is a different organic molecules. Okay, so each of these, you can see a small balls here and there. They are all different atoms. All right. So in these atomic simulations, you look at each atoms separately. All right. And so this is one example of the atomic simulations. All right. Okay. So, and the last thing is about the kinetic Monte Carlo simulation. I will talk about that, after, a little bit later. All right. Okay, so if you want to enjoy this kind of atomic simulation, actually it is important to imagine atomistic process of the certain phenomena. Like if you bend a solid beam, then the atoms, atoms within this beam, the atoms will deform, in a different way, all right? So, and or the burn by hot surface, if there's a very, the hot surface, then you can burn your hand by touching it. And, also, this hot surface means that these atoms are actually vibrating very widely. So by touching it, there's energy transfer from the hot surface, and so you can burn it. All right, or the melting of the sodium chloride in water. All right, you can imagine how the atoms will disintegrate when you put it into NaCl into the water. So, every process you can actually imagine the atomic process. Okay, and you can design how to simulate that using your atomistic simulations. Okay, so I want to emphasize here that always connecting this phenomena and atomistic detail is important to design your model system. Actually, that's the most difficult part of this simulation. Okay, so any question for the first part? here in this section, we want to connect this continuum simulations that is represented by finite element method and atomistic description. Okay, the same phenomena, but a different approach to look at the problem. Okay, so first, the question is that how these dopants, for example, you have the silicon wafer, and you put these dopants into some of the ion implantation, and you apply the temperature to move them around. Okay, so and you want to describe how this dopant will diffuse inside the silicon at a certain temperature. That is the question. All right, so the continuum description of this problem is that you start with the so-called fixed first law, which is that the current or particle flow or the flux is actually the negative of the gradient of the negative of the concentration gradient, right? Okay, and minus d times gradient C, and here d is the diffusion coefficient. I think that you are already familiar with this fixed first law. And also using this continuity equation, the divergence of the J is equal to minus the temperature partial derivative of the concentration, then you have the fixed second law. Okay, and for the one-dimensional system, you can solve this in analytical within a closed form, and it is obtained as the error function. Okay, as the function of the x over the square root t, right? And as a function of the temperature, the figure there. Okay, so this is the distance. So in the beginning, the concentration, all these particles was at a certain position, and as the time goes on, then you have this diffusion or profile of this diffusion or dopant diffusion. All right. So although this is obtained using using just analytic expression, but for the complicated system like a two-dimensional system or three-dimensional system, you can solve this same problem using the finite element method that I introduced in the last class. Okay. All right. And so, but what's so this fixed law is a very much powerful tool to describe the dopant diffusion or diffusion of the particles. So what's its limit? Its limit is that at a very small scale, at the nanometer scale, the individuality of dopants becomes significant. Okay, so at a very much small scale, like in recent modern day electronic devices, the electron channel is only some of the tens of nanometers thick, wide. It's very, very narrow. Right? In this case, you have to distinguish each dopant, all right, one by one, all right. And also, so in that case, the fixed law may not accurately describe the situation. And when the density of dopants is large enough, that interaction between the dopants, okay, so at a large concentration, the dopant will interact. But what is assumed in the fixed law is that the interaction between the dopant is completely ignored, right? They just pass through with each other, right? So that's that is actually implied within the linearity of this fixed law, all right? But however, at a very high concentration, dopant can collide, and that is completely ignored in the fixed law. And also, this is purely empirical. So for the bulk materials, although for some of the well-defined crystals, you can measure its diffusion coefficient quite accurately. But for example, in the grain boundary or the interface, the diffusion coefficient is not known, and it's very difficult to resolve the diffusion coefficient at such a specific configuration. All right. So this is meaning that this is purely empirical. So maybe an atomistic description may be necessary to deal with these kind of the problems. All right. So what's the atomistic view of the diffusion? How does the atoms diffuse actually within the solid? Okay. So in the gas phase or the liquid phase, atoms just move on, right? It's ballistic motion and collide and change direction. That's the diffusion. But within the solid, the diffusion is quite complicated. there are actually three mechanisms for the particle diffusion within the solid. The first one is maybe the most each one will be interstitial mechanism, where the dopant itself just pass through the bond through the empty space within the lattice. That's the interstitial mechanism. The vacancy mechanism is that there is a vacant site. So thermodynamically, every solid includes a certain amount of the vacancy, right? Because it's entropically always there is a certain amount of the vacancy, and by exchanging the site with the vacancy, it can easily diffuse, right? You can change its position, and then you have to keep in mind that there are many. Okay, so this is let's say that this is the vacancy. Let's say this is the vacancy, and this is the vacancy. All right, and this is dopant. All right. So first, it will exchange the site with this one. So this becomes vacancy, and this becomes the dopants. And then next, this vacancy will also exchange the site with the host atom, right? The silicon. As it is silicon, this is a vacancy. Then by exchanging it, this becomes a vacancy, and this becomes a silicon. Then at that, this dopant can diffuse or the change hop it into this vacancy. All right. So there are the vacancy or the same vacancy can be moving around, and then effectively the dopant can diffuse out. All right. So keep in mind that there are many certain number of the vacancies present in the solid. All right. So such a mechanism is so-called the vacancy mechanism, and the interstitial C mechanism is that unlike this interstitial C mechanism is that one of the interstitial actually push the atoms, and this atom is moved to the neighboring interstitial site. Okay, by this pushing mechanism, you can induce also the atomic diffusion. All right. So there are three different mechanisms that is played within the dopant diffusion, and the main mechanism actually depends on the dopant type, the size, and also the chemical nature of the dopant. All right. So in general, you have to include all of these mechanisms to accurately describe the diffusion process. All right, and this one shows that in a detailed view of the vacancy mechanism that I mentioned before. This is silicon, this is the boron, and this is the vacancy, and it's go here, and now the boron moves to the next site. Okay, and then furthermore, this is silicon. The silicon atoms also exchange the site, and the boron diffuses. Okay, so very complicated processes are occurring to induce this flow of the boron diffusion. All right. So this is the atomistic view of the diffusion, and each of the hopping process is actually it involves certain the breaking of the bond, or the breaking or the forming of the atomic bonds. For instance, in this case of the interstitial mechanism, this dopant, in order to move to the next dopant site, like from A to B, they are equivalent, right? A and B are equivalent, but in order to go through it, you have to push these two silicon atoms apart to go through between them, right? So in doing so, you are actually breaking this silicon-silicon bond, and it costs certain amount of the energy. And so the energy is usually goes up and go down, right? So this energy is called activation energy or the diffusion energy. All right. So so this is the activated process. So it needs to some of the thermal energy to go over this energy barrier. All right. So it should be a thermally activated process. So I'm not going through these details of the deriving this equation, but by making use of some of the thermodynamic consideration and the statistical mechanics, and you can actually derive that because of that activation energy, the rate of the jump. So how many times of the jump it will jump per each time, it actually depends on the most importantly exponential of this activation energy divided by minus of the activation energy divided by the temperature. All right. So this is the Boltzmann factor, and times another important thing is that this is the so-called attempt frequency. So the thermally, if you observe, if you look at these atoms, and actually the vibrate at the finite temperature, it will vibrate, widely, and then at a certain time, it will happen to have a certain enough amount of the energy, and it will go over those energy barrier, right? So this the number of the vibrational frequency, it actually also the scale with the rate of the jump, and this is typically similar to the phonon frequency, which is about the terahertz. Okay, so 10 to the 12 times per second. Okay, so once you know this activation energy, which you can obtain from the atomistic simulation, and also you can obtain this. You can use some of the approximate value, but you can also obtain quite the accurate value by just look at this from this atomic simulation. And so these both quantities, mu naught and EA, can be obtained from the atomic simulation. All right, and so that's the for just one instance of the diffusion, one jump process. For the diffusion, you need to have a combination of the many different independent jump, like n jump, and so now it corresponds to the random walk, not the random walk problem, random walk. 일이 아니고 걷는 거. I'm sorry that mistyping. Random walk problem. 무작위적으로 걷는 random walk problem이 되겠습니다. Okay, so now you can combine the rate of the jump with the random walk problem, and you can obtain the average diffusional length as a function of the temperature. All right, so I'm not going through these details, but if you're interested, then you can follow it without quite easily. And this root mean square displacement is now about proportional to square 2D, and so you can obtain this diffusional coefficient from this our expression of the A is the lattice parameter, and the mu naught is the phonon frequency. A is the certain constant, so actually this is correlation constant, which is well known, and also the activation you can obtain from the simulation. So every quantity here, actually you can obtain from the atomistic simulation. All right, so there's no you can completely exclude those empiricism in your simulation. All right, and also because of this exponential nature, if you plot the log of the diffusion coefficient at 1/t, then you can obtain the activation energy, and you can compare with the experiment. All right, so that's that shows how we address the same problem using the atomistic viewpoint, right? It's much more complicated than the fixed law, right? You have to go through very many different types and very complicated calculations. However, what we obtain here is the very precise theory, right? Without any empirical parameters, right? So that's the strong point of the atomistic simulation. So it is very general, and it can be used to in many various kind of configuration, not just the solid, but also the grain bounded of the surface. All right, so that was the comparison between the continuum simulation and atomistic simulation. All right, then how we can describe these atomistic simulations? We will start with the most simple example of the one-dimensional harmonic oscillator, right? Let's say that there is a mass m that is attached to spring with a spring constant of the k. And the question is that what is the, given the initial condition x naught and v naught, initial position and initial velocity, what are the position and velocity at later time, t, right? A simple question. Of course, if you have learned it, you have learned this problem in general physics, and you can. We have already know this analytic solution in the bottom, which is combination of this sinusoidal sine or cosine. Okay, so sinusoidal motion, and it's a frequency. The angular frequency is the square root of the k over m, and the period is 2 pi times of the m over k. Okay, so this is analytic solution, and so you know what is the exact solution. Now we try to solve this using the computational or the numerically, right? So in solving this numerically, the first step is to discretize your time domain. Okay, so you cannot describe the continuum variable in the computers. In computers, everything is digitized, right? So therefore, you have to discretize your time domain. We slice the time at every temperature, at every time delta t, okay, and describe its motion only at this time, 0 delta t, 2 delta t, 3 delta t, etc. Okay, so we are only concerned about this position at this time. Okay, so then the question is that this is a kind of a consecutive equation, and so the question is that given this given this the position and the velocity at the time t, what is the how we can obtain this position and the velocity at the t plus delta t? All right, so that's the question that we are converted from this Newtonian mechanics. All right, so here always the basic tool is the Taylor expansion. We expanded this xt plus delta t around xt using the Taylor expansion, and you have xt and x prime t delta t, and x2 prime and 3 prime, etc. Okay, so you can expand it, as much as you want. And here this x prime t, which is the time derivative of position, this is nothing but the velocity. All right. And what is this x2 prime t? The second derivative of the position is what? Is what? 뭐죠? Acceleration, 그죠? If you take the second derivative of the position, it corresponds to the acceleration. So f over m, f equals ma, so f over m, all right? And you ignore this, the remaining terms here. Okay, so this is the thing that we can keep at this moment. And we neglect the other term, and this is called the truncation error, right? In the Taylor expansion, you have to ignore a certain the rest of the terms, and that is called the truncation error. And about the velocity, you can also do the similar thing. And in here we have an explicit expression up to the v prime, so which is again this is acceleration, and therefore this is f over m, right? And so here we have a truncation error of the order of delta t square, which is actually more serious than the position. Okay, so anyway, let's ignore these terms, and let's assume that this velocity t plus delta t is given by vt plus f over m times delta t. All right, so therefore, once you know this position and the velocity at the time t, then since you know this position, then you can know the force, right? Because force is nothing but F equals minus kx, right? From the Hooke's law, F equals minus kx. Therefore, if you know the xt, then that means you know the force at the same time, t, okay? So, therefore, you know the ft. So, using this equation, so everything is known, right? The velocity, force, and so everything is also, you can predict from this expression about this, what is the position and the velocity at the t plus delta t. All right? So that's the procedure that you can apply in this calculation. All right, so what's the solution? So what's the numerical solution? Let's say for the specific example, here the mass, the spring mass is 25 gram, and K is Newton per meter, and X naught is 10 centimeter, and you have released without any initial velocity. All right. So in this case, the time period is about 1 second. All right. So and these results are the numerical solution that we have applied that obtained from the formula in the previous slide using the different time step. So at the top, the time step delta t is 10 to the minus 4 seconds. Okay, it's a very short time scale. It's 0.1 millisecond, and this analytic solution is in green line, and this numerical solution is actually this is a red dot here. And you can see at the top is the position, and this is velocity. You can say it's pretty good agreement. All right, you cannot distinguish. There's a slight mismatch, but you cannot distinguish, up to 10 seconds. All right. Okay, so 10 to the minus 4 seconds is acceptable. But how about if you increase the time step delta t? Because, for instance, in order to simulate the 10 seconds, if the time step delta t, time step is 10 to the minus 4 seconds, it means that you have to calculate 10 to the 5 times, right? 10 to the 5 times, or 100,000 times, okay? Which is quite many iterations. And by increasing the time step 10 to the minus 3 seconds tenfold, then you can actually reduce number of iterations by 10,000, all right? So if the first calculation ends at let's say only 10 minutes, then the second calculation can end at one minute, okay? So it is always, what we preferable to increase the time step. So in this case, but here you can see that in the beginning it's okay, it looks okay, but as time goes on, this discrepancy between the numerical and analytic solution is getting bigger and bigger. All right, and you can see actually more dramatically at the bottom when you increase the delta t time step by 10 to the minus 2 seconds. Then you have the dramatic discrepancy, and actually this deviation, it actually increases with time, right? So this means that the simulation fails, all right? So what we can learn from this example is that the time step should be small for the sufficient accuracy, all right? The small is always more accurate, usually. But the problem is that if it is too small, then it takes too much longer time, right, for the actual computation. And for any time step size, if you go through the many iterations, then this error becomes accumulated. Error becomes larger and larger, right? For the very small time step, you cannot notice it very well. But for instance, if you go like 10,000 step or 1 million step, then you will see actually some of the discrepancy. All right. So those are the things. Okay, so this is does not look good. So you want to improve our method. The problem is that the velocity part. So the previous formulation here, you can see that this velocity, in Taylor expansion of the velocity, you have included only the term up to the first order, which is very inaccurate, and so you want to improve it. So one thing that you can do is to include the second derivative, and in order to include the second derivative of the velocity, you expand the force, Taylor expansion of the force. 이렇게 뭐 끝났네 이거? 꺼졌는데 이거? 꺼져도 괜찮은가? All right. So by expanding the force by expanding the force, you notice that there is a first order derivative which corresponds to the second derivative of the velocity. All right. These two are actually equivalent, and therefore you can obtain this f prime t is mv2 prime, and therefore this v2 prime is, you can know this by take the difference of the ft plus delta t minus ft. Okay? But how we know this ft plus delta t? You can know it. Well, first by applying this Taylor expansion on the position part, then you can obtain this x t plus delta t, right? So you know the position at the t plus delta t. And if you know the position, then you know the force, right? Because F equal minus kx, you know, okay? So by know this force, now you can use this formula, right? By use this formula to improve this accuracy in the description of the velocity, right? And now the error is reduced down to one order, by one order, as order of delta t to the third, all right? And so this technique of the improving the accuracy in the velocity is called the velocity-Wallet algorithm. The Wallet is the name of the people, the person who invented it. And numerically, this is the correspond to the so-called predict correct method, the numerical analysis. Okay, so how does it perform? This is for the same problem that we have seen before. We have now applied this velocity-Wallet algorithm. Now about the time step. So remember that this simulation failed at around 10 to the minus 2 second, right? 0.01 second. But using the velocity-Wallet, you see that almost perfect agreement with the green and red dot. Okay? So for the same problem, right? Just by adding one more Taylor expansion, then you have obtained much more accurate, the simulation. All right? And you can even further increase the time step, like 0.05 second, right? 5 times. Then you can have see that still this red dot follow red cross, this follow this another solution pretty well. Right? However, if you increase further, like the 0.1 second, then, well, it oscillates quite reasonably, but you can see that because this frequency is slightly different, and so it is a little bit retarded than this analytic solution, right? So from the simulation, you can see that, okay, so this one oscillation takes about 1 second, right? 1 second. And so this is for 1 second, you are describing 100 times for one oscillation. In this case, you are describing one oscillation by 10 times, or 10 step. Okay? So 10 step is a little bit push the limit, or push the accuracy. All right? So maybe you can see, so for the vibrational frequency, or the period, for one period, it is a reasonable choice to take about 1/10 of the time step. All right? Okay. So that gives you an idea about how to take the time step in the atomistic simulation. For most of the small molecules, the fastest or largest or highest vibrational frequency is about 10 to the 13 to 10 to the 14 hertz. Or 100 to or 10 to 100 terahertz, right? Or for example, in the case of the H2 molecule, this vibration frequency is around 10 to the 14 hertz, right? So it means that 10 to the 14 hertz means that the atoms vibrate. So 10 to the 14 hertz means, okay, so atom vibration 10 to the 14 times for 1 second, right? Which means that the period, one oscillation period is what? This 10 to the 14 hertz means that one period is that, because 10 to the 14 hertz correspond to 1 femtosecond, right? 10 to the minus 15 second. 10 to the 14 hertz means that the period, oscillation period is about 10 femtosecond. All right. So this is the fastest time constant for the vibration, or shortest time constant for the vibration of the most of the molecules and also the solid. Okay. So therefore, adequate time step for the atomistic vibration simulation is the 1/10 of this time scale which which is the 1 femtosecond. All right. So therefore, for the atomic simulation, you cannot increase the time step well above the 1 femtosecond. That's why we are actually limited by our simulation. If we go original slide, okay. So this is fast. So we start from the femtosecond, right? You cannot start from, let's say, the picosecond. All right. So every time step takes about 1 femtosecond, and so in order to simulate the nanosecond, we have to go 1 million time step, which is extremely, large number of the iterations. Okay, so that's the main reason why we cannot simulate, sufficiently long time scale. Okay, so all right, so using this simple, I am not going to discuss. So there's another, the Vallet algorithm, but I will skip this part. I will just mention the velocity Vallet. And about, also we are interested in the energy, right? We are besides this atomic trajectory, we are also interested in the calculating energy. Therefore, we are concerned with the energy. And about the energy, there is kinetic energy, and also there is the potential energy, right? And you know that the total energy, which is the sum of the kinetic and the potential energy, they are the constant value, right? And on the simulations, of course, you can see that always this total energy is conserved. All right. So how about this more realistic system? Let's go for a more realistic system. The next thing is that this is a two-body system where these two atoms are connected with one spring. Okay, so in this case, you have the total energy, and let's assume that this is moving just one direction. Okay, in this case, the kinetic energy is the sum of the kinetic of the first atom and the second atom, right? So half of the mv1 scale, m1 v1 scale plus half of the m2 v2 scale. And also there is a potential energy that is stored in this spring here, and it can be expressed by half of the k times x1 minus x2. This is the distance between these two atoms minus d square. 여기 이제 녹음 안 되는 건가 이제? 모니터가? 오케이. Alright, so in order to know this force, what we usually do is to take the partial derivative of the potential energy, and you can obtain this force, and by applying the velocity Vallet algorithm or Vallet algorithm, you can obtain this trajectory. You can find the trajectory at a certain temperature, a certain time, t plus delta t, using the position t and t minus delta t. Here, okay, pretty similar thing. But once you know this potential energy, you can derive, by taking this partial derivative, you can obtain atomic force. All right, and in the case of the three-dimensional system, and there are many particles or systems of particles, and they are connected with pretty different pairs of the spring. Okay, so in this case, you can just simply generalize your original formula that this potential energy is the sum of the old spring, the potential energy of the old spring, like in here. Okay, Uij is the spring, the potential energy of the spring at the connecting these two I and J atoms. Okay, and by taking the partial derivative, you can obtain the force. Right. So even though it's much more complicated, you can simply apply the same formula, the velocity Vallet or Vallet algorithm, to describe this atomic motion of your system. Okay. Okay, so the remaining question is about interatomic potential. Okay, so about the potential. What is the, so in the previous slide, so we have simplify the interaction between the two atoms as one single spring. But then what is this? So what is the spring constant of this interaction? All right. So that is the called this the potential that applied between the two atoms is called interatomic potential, or sometimes it is called the force field. All right, because it gives you the force by taking a partial derivative. For example, in the case of the H2 molecule, when they form a bonding, so if the two hydrogen-hydrogen atom forms a bond, from this very accurate quantum mechanical calculations, you obtain this line of the potential energy. All right. So this is the interatomic potential of this H2 molecule. All right. So, but this is the quantum mechanical calculations. And here we are, since we are using the classical or empirical atomic potential, we have to simplify the calculations, and we have to assume certain functional form that describe the interaction between the two atoms. All right. Okay, so the functional form of the interatomic potential actually depend on the chemical nature of the atomic bond. And it is different. It depends on whether it is ionic bonding or covalent bonding or metallic bonding. Okay, and I will explain them one by one. So first one is the van der Waals interaction. So van der Waals interaction applies between inert gases or organic molecules or the adhesives. Okay, or the polymers, and its physical origin is the spontaneous polarization of electron gas. Okay, so interaction is usually weak, but since they are additive, okay, always van der Waals interaction is additive. So if we have the larger contact area, then this van der Waals interaction always increases. It dominates other force. Okay, this van der Waals interaction is well approximated by so-called Van Allen's potential, or 12-6 form, which is the VL equals, there's epsilon and the sigma parameters with this functional dependence, and its form is like that. Okay, here. All right, and so this solid line of the experiment. Okay, so the solid line is experiment over very precise argon potential that is applied between argon atoms, and you can approximate this solid line using this van der Waals type functional form as indicated by this dashed line. And the parameters that for the VD parameters are for epsilon is this one and sigma is this one. Okay, so this van der Waals interaction most well followed by the inert gases, and parameters between them are very well known. Okay, so this is the one. This is the first type of the interatomic potentials. All right, and once you know this van der Waals interaction, then you can obtain actually lattice parameters and also the cohesive energy. But I will just skip this part because of the time limit. I'm sorry about that. Okay. And the second, ionic bonding. Okay, if your material is highly ionic, like ionic crystal of the Na plus and Cl minus, and also between the polar molecules, then its interaction between the atoms are mostly dictated by electrostatic energy. And you have your functional form, interatomic potential should reflect that. Okay, so here this is the Coulomb interaction between the two ions with the charge of the Gi and the Gj. Okay, but if you include only this electrostatic part, actually because of this one-over-r nature, this is a singular. So if your r goes to 0, this interaction goes to minus infinite. Therefore, whole solid will collapse. Right? But that does not happen. Why? Because each atom, there is an electron, because of the Pauli exclusion principle. Okay, so the atoms actually repel each other at the short distance. So in order to have such a short range recursion, you are including certain empirical form, or that gives you a positive interaction between the two atoms, all right? So therefore, this term is necessary to prevent the collapse of the whole lattice, all right? And also, since every atom has the van der Waals interaction, you also include this long-range interaction of the Lagrange type, R to the 6, right? All right. Okay. So this is the and then one thing that you may need to keep in mind is the Coulomb potential. This potential is long-ranged, meaning that because of the van der Waals nature, its interaction goes too far away. So you have to include the large number of the atoms to get this to get the right the energy. All right. So that's one actually the difficulties in calculating the energy in the ionic bonding, the long-range nature. Okay, so one thing here, one problem of such a model is that here this in this model, it assumes that the charges are just point charge, like one that is localized at one site. However, in actually, these charges are actually is atomic electron cloud, and under external electric field, it actually is slightly polarized. Okay, so therefore, in order to be more accurate modeling, you have to include this polarization of the atomic cloud on top of that point charge model. Okay, so sometimes when you want to higher accuracy, then you can include this polarizable, so-called polarizable force field. 이것도. Okay, so this slide was want to discuss that 이게 지금 그러니까 이게 좀 파일을 갖다가 딴 데서 가져온다고 이게 지금 이게 일단 맥북에서 이제 맥 컴퓨터에서 이걸 에디팅을 하는데 그게 윈도우로 가져오면은 이렇게 어긋나져 있어요. 그림이 좀 이렇게 엉뚱한 데로 스크린 캡처하기 엉뚱한 데로 가 있어가지고 좀 이해하기 바랍니다. Okay, so but here to make the story short, what I want to emphasize is that the charge is actually is not that simple or the fixed quantity. For example, this is the interaction of the magnesium and oxygen in the MgO, which is very well known, ionic solid. So nominally, maybe you think that magnesium is 2 plus and oxygen is 2 minus. All right, it's just nominal charge. However, if you use such a value in the as a G in the ionic potential model, then this is the energy when you on the surface when you pushed out this magnesium or oxygen from the surface, the energy increases. This is the what it describes here, and this accuracy value from the quantum mechanics calculation is presented by this dot, the black dots. But if you use this fixed charge of the 2, then it overestimates such an energy increase, and you have to decrease the charge down to 1.2, then you obtain this reasonable description of the energy increase, which means that this is the chemical nominal charge is not the actual or precise value then you put into this ionic the model. All right, so it should be tuned, right, depending on the system or depending on the situation. All right, and the next is the covalent solid. In the case of the covalent solid, which is most well represented by the silicon or the carbon or silicon carbide, the characteristics, one character of the characteristic feature of this covalent solid is that its bond strength depending on the neighbor, right? For example, in the case of the carbon, the diamond, which is the sp3, the bonding, the bond length between the carbon-carbon is 1.54 angstrom. On the other hand, in the case of the sp2 bond in the graphite, it is reduced to 1.42. In the case of ethylene, double bond 0.34. In the case of acetylene, it's triple 1.2. Okay, so by increasing the order, the bond order, then this is the interaction between the carbon-carbon becomes stronger. All right. So your interacting potential should reflect that feature, and the one well-known type of the potential form is so-called Tulsa potential, which is Tulsa is the famous guy in IBM, and he has invented the functional form that interaction potential consists of the repulsive and attractive part, and this attractive part is actually is prefactor depending on the bond order or its environment. How many neighbors or how they are distributed around a certain atom, it affects this V value, right? And so such that at a higher bond order, you have the more stronger attractive interaction between the carbon-carbon atom. So this is called the Tulsa potential, all right? So, but I will not show you for the complete, it's mathematically quite complicated mathematical formulas, but I will skip that. One caveat is that actually many of the ceramic materials are actually not purely ionic or purely covalent. Actually, many of these semiconductor materials are actually the mixed type of the bonding between the ionic and the covalent. And therefore, for instance, silicon dioxide, zinc oxide, gallium nitride, gallium arsenide. So in this case, besides such an Tulsa type potential, you also have to include a small amount of the ionic potential to get the right description of the atomic bonding. All right. So there's also another type of the force field that developed for this kind of the material. And lastly, the metallic bonding. So it applies to most of the metals and alloys, and it works better with a compact structure like FCC or HCP rather than BCC. In the case of the BCC, we have a little bit of like iron. We have a little bit of this covalent nature, which you have to take into account. The nature, the physical origin of the metallic bonding is that electronic kinetic energy of the electrons are lowered by forming the bond, right? Like scale well model. Scale well model, for example, the lowest energy state, the energy is lower for the wider quantum well, right? Because kinetic energy is decreased, right? It's pretty much similar like that. By forming these atoms and the electrons are moving around in a large field, like free electrons, then you can lower the kinetic energy of dramatically. That's the main driving force of the metallic bonding. And the functional form that is most compatible with such the metallic bonding nature is called embedded atom model potential, where this potential consists of some of the repulsive part and the pairwise part, and also so-called this embedded atom part, which is that the idea is that in the metallic bonding, it always they want to increase the electronic density. That's the main the driving direction of the bonding. That they want to increase the electronic density. All right, and so basically this density function means that when there is a certain atom, there are neighboring atoms. 여기 뒤에서 잘 보이세요? Okay? Alright. And each atom contributes a certain amount of the density to the atom that we are interested in. Right? Okay, so those atoms that are farther away, they will contribute very small amount of the electron density. And for the atoms that is close to the atom, then it will contribute the more electron density. All right? So, and then you add up all these density at a certain position, right? And it corresponds to this low I. This electron density contributed by other atoms at a specific site or specific atomic site. And you have this function. And for the higher density, you have the lower energy because it is minus, all right? For the higher density, you have the lower energy, all right? So this part actually drives the system to have the larger electron density together, all right? So this is called, following the inventor's name, it is called the Finite and Sinclair type interatomic potential. This is the best functional form for the metallic bonding. Okay? All right, so, and about the molecular system, you have, for instance, the water molecule. We have various kind of electrostatic potential and also the van der Waals potential and also the spring constant that correspond to interatomic, this the bond strength and also this angle. Okay, water molecule can flip, right? And so this angle term indicates that this flipping motion of the water molecule. Okay, and for about the water, people have seriously studied a lot of simulations, and they have found very optimized parameters for the water molecule, solely for the water molecule, and this is most well known. The potential is a tip 3p model for the water. Okay, and so basically what I want to emphasize is that each different functional, each different type of the atomic interaction, you have a different form of the mathematical formula, and by fitting certain properties, then you can obtain those parameters. Okay, and then you use that for the later simulation. Okay, so one problem here is that you need to know beforehand what is its functional form, right? So in the case of metallic bond, you first start with a certain functional form like here, and also in the case of the covalent solid, you start with this certain type of the potential, etc. Right? So the problem is the main difficulties in the force field is that you have to know certain preset functional form to begin the simulation, right? But in general, like as we've seen this mixed type of the bonding, such a mathematical formula is usually difficult to find beforehand, right? So very recently, people, including us, what we are trying is that we develop interatomic potential that does not assume any kind of the functional formula, and just learn interatomic potential from the reference data set using like AI type machine learning or here the neural network potential, and just train this reference data, and you get this neural network that can simulate, best mimic this reference data set. Okay, so in this kind of approach, this is very recent development of the interatomic potential. Here we do not assume any kind of the mathematical formula beforehand, and therefore it is very flexible and it can be applied to any kind of the materials. So this is one hot topic in our field, and we ourselves, the TAs in the back, they have developed this atomistic potential package that using this neural network. And so if you are interested, okay, so ask them. All right, so this is the one new topic. And lastly, I will briefly talk about this period boundaries, but I think I can discuss this last part in the next class when we talk about work structure. Okay. All right, so I'm sorry that I have hasted too much. All right, and maybe the tutorials they will show you how to install the lens package. But before that, if you have any question, okay, please.